Welcome to online classes. Dear students, today we are going to discuss low pressure and low temperature. This topic is for BSc second sem students of 2019-20 batch. This is from Department of Physics, Nehru Arts, Science and Commerce College, Gandikeri, Hubli. Dear students, we are discussing the low pressure and low temperature chapter. What causes the pressure of air on earth? Consider the earth and atmosphere on the surface of the earth. The height of the atmosphere is about 12 kilometers. Now, if you imagine the air column of the atmosphere, it puts a pressure on unit surface area on the earth. Now, the force of this air column on 1 meter square area of the earth's surface itself causes the 1 atmospheric pressure. So as pressure is equal to force per unit area. Now, how much is 1 atmospheric pressure means? So already it is calculated. 1 atmospheric pressure is equal to 1,1325 pascals. So what is 1 pascal is? 1 pascal is 1 Newton force per 1 meter square area. What is 1 Newton force? It is equivalent to the weight of 1 kg of substance. That means 1 atmospheric pressure is equal to, as it is 1,1325 pascal, it is equal to 1,1325 kilograms of substance. That means it is equal to weight of the 10 cars of approximately 10,100 kg each. On 1 meter square surface area. Just imagine how huge is the 1 atmospheric pressure means. How do you measure it? It is simple. Take a 1 meter length test tube, completely fill it with mercury and invert it in the mercury bath. And now the height of the mercury column inside the test tube will come down and stops. If you measure the height of that column from the surface of the mercury in the bath, it will be about 760 mm. That means 76 centimeter. What makes the mercury to remain above the surface of the mercury outside? So that is due to atmospheric pressure exerted on the surface of the mercury outside the test tube pushes the mercury inside this test tube. And there is no downward atmospheric pressure as there is a vacuum here. And only the pressure from bottom to top. So that holds the weight of this height of the mercury column, which is equal to 760 mm. What is the weight of this mercury column? That can be calculated using this formula, that is density of the mercury into acceleration due to gravity, height of the air column. So 13.6 thousand, that means into 10 power 3 kg into is the density of mercury into 9.81 meter per second square is the acceleration due to gravity, and 76 centimeter means 0.76 meter is height of the mercury column. If you calculate it, you will get 1,01,396 Newton per meter square or pascals. Dear students, let's understand what is low pressure. If the air is pumped or sucked out of the closed volume, the low pressure is created in that volume. Low pressure is created using vacuum pumps. Simple example to understand how vacuum pump works is, look at the fan fitted in kitchen, which propels the air from inside the kitchen to outside. You can see in this picture the most commonly used vacuum pump, that is rotary vane pump. There are so many applications of vacuum pump. It is used in many industrial and scientific processes, including composite plastic molding processes, production of most types of electric lamps, vacuum tubes, and CRTs, where the device is either left evacuated or refilled with a specific gas or mixture, semiconductor processing, notably iron implantation, dry etch, and physical vapor deposition, atomic layer deposition, and plasma enhanced chemical vapor deposition, in photolithography, electron microscopy, medical processes that require suction, medical applications such as radiotherapy, radiosurgery, and radiopharmacy in uranium enriched instrumentation to analyze gas, liquid, solid surface, and biomaterials, mass spectrometers to create high vacuum between ion source and the detector, vacuum coating on glass, metal and plastics for decoration, for durability and for energy savings such as low emissivity glass, hard coating for engine components, ophthalmic coating, milking machines and other equipment of dairy sheds, vacuum impregnation of porous products such as wood or electric motor windings, air conditioning service, uh, and compactor, vacuum engineering, sewage systems, freeze drying, and fusion research in the field of oil regeneration and re-refining. Vacuum pumps create low vacuum for oil dehydration and high vacuum for oil purification, especially in the field of transformer maintenance. Vacuum pumps play an essential role in transformer oil purification plants, which are used to extend the lifetime of transformers in the field. Vacuum may be used to power or provide assistance to mechanical devices. In hybrid and diesel engine motor vehicles, a pump fitted on the engine, usually on the camshaft, is used to produce vacuum. In petrol engines, instead of vacuum, is typically obtained as side effect of the operation of the engine and the flow restriction created by the throttle plate, but may be also supplemented by an electrically operated vacuum pump to boost braking assistance or improve fuel consumption. This vacuum may be then used to power the following motor vehicle components: vacuum servo booster for the hydraulic brakes, motors that move dampers in the ventilation system, throttle driver in the cruise control, servo mechanism, door locks, or trunk releases. In an aircraft, the vacuum source is often used to power gyroscopes in the various flight instruments to prevent the complete loss of instrumentation in the event of electrical failure. The instrument panel is deliberately designed with certain instruments powered by electrically and other instruments powered by the vacuum. Exhaust pump and their characteristics. An exhaust pump is a device to exhaust or remove air or gas from vessel. It is based on three important characteristics. Number one, exhaust pressure. Number two, degree of attainable vacuum. Number three, speed of the pump. Now let's understand what is exhaust pressure. Exhaust pump consists of inlet or intake through which air or gas enter into the vessel, and an outlet or exhaust side into which the air gas drawn from the vessel is expelled. The pressure on the exhaust side is referred to as the exhaust pressure. It may be equal to the atmosphere or may be reduced to a fraction of the atmospheric pressure by means of an auxiliary pump called a rough or braking pump. In general, the higher the degree of vacuum required on the intake side of the pump, the lower must be the exhaust pressure. Second one is degree of vacuum attainable. This is defined as the lowest pressure which may be attained in a closed system connected to the pump. It is found that this limiting pressure depends upon the exhaust pressure, and it is due to the leakage is most noticeable when the light gases like hydrogen and helium have to be pumped out of a closed vessel. The next factor is speed of the pump. The speed of the pump may be defined as the relative rate of reduction of pressure in a given volume. Let P naught be the lower limit pressure and attainable with a given pump, and P be the pressure at any instant time t in the vessel of volume V connected to the pump. If S be the speed of the pump at pressure P, and rate of decrease of pressure in the vessel is given by a simple equation, minus dP by dt is equal to S into P minus P naught divided by V. Call it as equation 1. This can be written as minus dP by P minus P naught is equal to S by V into dt. Call it as equation 2. Let P1 and P2 be the pressures at instants of time T1 and T2 respectively. Then integrating the equation 2 from the limits P is equal to P1 to P is equal to P2 and time T1, T is equal to T1 to T is equal to T2. The integration looks like this. Minus log of P minus P naught with the limits P1 to P2 is equal to S by V into T from limits T1 to T2. That is equal to log of P1 minus P naught divided by P2 minus P naught is equal to S by V into T2 minus T1. That S will become equal to V divided by T2 minus T1 log of P1 minus P naught divided by P2 minus P naught to the base E. Let's call this as equation 3. If the limiting pressure P naught is very low in equation 3, the P naught becomes 0. We can write S is equal to V divided by T2 minus T1 into log of P1 by P2 to the base E. This is equation known as Gedde's equation, which is defined for S, the intrinsic speed of the pump. If P1 by P2 is equal to E and T2 minus T1 is equal to 1, then we can write S is equal to V. Thus, the intrinsic speed of the pump is equal to that volume in which the pump will reduce the pressure to 1 by eth of it, that is 36.79% of its instantaneous value in 1 second. The actual speed of exhaust E at any instant is defined by Langmuir as E is equal to V by P into dP by dt. Let's call this as equation 4. Then E is equal to V by P into dP by dt. If dV be the volume of the gas at pressure P extracted from the volume V during the time interval dt, then PV is equal to, in place of P we can write P minus dP, in place of V we can write V plus dV, as pressure decreases as volume increases, is equal to, multiply the bracketed terms, you will get PV plus PdV minus VdP minus dP into dV. Now PV on both the sides will get vanish, and what remains will be PdV minus VdP minus dPdV is equal to 0. Neglecting the small term dPdV, as a product is very very small, PdV is equal to VdP. Then dV will be equal to V by P into dP, and divide throughout by dt, you will get dV by dt is equal to V by P into dP by dt. Let's call this as equation 5. From equation 4 and 5, we can write E is equal to dV by dt. Thus, the speed of the exhaust pump may be defined as the rate of change of volume of a gas in the vessel at any given instant, the volume being measured at the pressure attained by the pump at the instant. Substituting the value of dP by dt from equation 1 in equation 4, we will get E is equal to V by P into S into P minus P naught by V get cancels. That becomes equal to S into P minus P naught divided by P. Again, if you divide P to P and P naught separately, and get E is equal to S into bracket 1 minus P naught by P. This relation shows that in the beginning of exhaust, P is very large compared to P naught, so that P naught by P is practically 0, and hence E is almost equal to S. That is, in the beginning, the exhaust speed of the pump is equal to its instantaneous intrinsic speed. As P approaches P naught, E decreases and finally becomes 0. Then P is equal to P naught. That is, pump loses all its exhaust speed at the lowest attainable pressure.